Hi everyone, my name is Charlie Tran. I would like to present my research on representation learning from medical images. I am proud to present this as a member of the UF McNair program and the UF Smile Lab mentored under Dr. Fink. Deep learning is a subset of AI. We first questioned how can we make deep learning practical for society? We then questioned what are the current problems and limitations of deep learning in the medical field? This brings us to the contrast between supervised learning and unsupervised learning, where in supervised learning, we are solely working with labeled data. With unsupervised learning, we are working with unlabeled data. Now, this difference is very important. We seek unsupervised methods because they reduce the amount of human work necessary. Take a look at the datasets below. For example, in the Cypher10 dataset, this is a natural dataset of images such as cats, birds, planes, and so on. These are easy to obtain, label, and work with. However, when we utilize medical data sets, you can think of CT images, MRI images, and so on, we are bounded by the amount of data that we are given. This is because it is not common for this data to be publicly available. It is not common for a doctor to diagnose an image, record these results, label them, and publish them for people to use. This difference between unsupervised learning and supervised learning changes how we design our models, the performance, the computational time, and so on. Therefore, we seek an unsupervised model that works independently of human effort that works well in the medical practice. Developing a neural network takes not only mathematical understanding, it can be improved by an understanding of neuroscience mechanisms. We look to derive some inspirations from neuroscience as a way to bridge the gap of our understanding between the two. The purpose of the study is to develop an unsupervised deep learning model that outperforms existing methods with significantly reduced data. This research has special focus to the medical community to initiate AI-supported diagnosis of health conditions as a valuable tool to doctors and patients for accurate and fast diagnosis. I discussed some consensus of how unsupervised methods have been developed recently, with specific focus on the task of image classification. The idea is that there are intrinsic characteristics of an image that are most significant to classifying it. That is, no matter how you augment an image, your underlying representation should be the same. This framework came to be known as contrastive learning. We are effectively running two neural networks on two augmented views of an image, measuring the similarity between each other, and training the network to minimize the differences between each other. In doing so, we are training the network to develop and recognize the representation of an image, where we extract the qualities of image as a way of automatically classifying and diagnosing it. In the technical details, we train the network in an unsupervised manner, freeze these model parameters, and train a linear or nonlinear classifier as a tool for evaluating the accuracy of a model's ability. Now for this project, I have worked with several data sets. I would like to share one specific application, which is on the fundus data set, along with some preliminary results and details below. The goal on this data set is to design a network that can assign a score between 0 to 4, measuring the presence and severity of diabetic retinopathy. I shared some comparison between unsupervised, supervised, and semi-supervised frameworks from the literature by evaluating on a metric known as the AUC score. If you're unfamiliar with the AUC score, you can think of it as being similar to accuracy, but not exactly the same, where a score of 0.5 is random guessing and a score of 1 is perfect evaluation. We demonstrated the success of unsupervised models, again taking note that this is utilized on unlabeled data, the raw images themselves. We showed that by leveraging some labeled data in conjunction, which is the semi-supervised model, you can improve the performance of a network as expected. Admittedly, there are some flaws in these results. However, I consider these acceptable as a preliminary basis for results. Here I present the results from the table before in graphical form. The AUC scores, as we saw, range from about 0.53 to 0.77, depending on which methods we use. Certainly, there is still a large room for improvement. However, when you look at these results, think, could even an experienced doctor diagnose an image perfectly all the time? Will the same diagnosis be consistent among all doctors? Certainly not. When you consider these problems and the room for improvement left for deep learning, we are seeing the potential of deep learning for medical tasks. As for future work, I am looking towards designing a novel network that is specialized to the medical data sets and demonstrating the minimality of data necessary to achieve high performance. Additionally, I'm looking towards developing a link between the neural network framework and neuroscience mechanisms. I would like to acknowledge and give thanks to my PhD mentor, Peng Liu, and undergraduate members of the SMILE Lab, specifically Jason Chen, and as well as my mentor, Dr. Fang. I would like to give one last thanks to the McNair program for giving me this opportunity and aiding me in my research all the way through. I'd like to give some references for some methods throughout the literature and also some references for figures that I've used throughout. Thank you very much. That's all.